Alrighty, happy Thursday. Here. All right, so we've got maps and hash tables to talk about today. Again, we're going to skip over skip lists. It's a cool topic, but we don't need to get too deep into it here. So the idea with a map and a hash table is how dictionaries work. So a Python dictionary is actually known as a map. And it's some value relates to another value. A key maps to another value. That's what a map is here. And a hash table is an efficient way of storing these sorts of things. So again, you can get into the inefficient ways of storing things if you want. I'm not very partial to looking at how to do these badly and then look at how to do them goodly is the wrong word, how to do them right or efficiently. So we'll look at the efficient way of storing it mostly. And then when we get to lab next week, we'll look at probably the better way of doing these things. We'll kind of tweak it a little bit here. So this is week 11. I'm going to do maps. There we go. Lost my window. All right, so in Python, again, it's a little silly to build these out yourself because they're built into Python by people who are really smart. The idea is if we understand how they're written, hopefully we understand their performance better. And that's sort of the goal. And that's why we look at all these data structures, because the way that we store and interact with the data performs differently based on which structure we're using. And the goal is we use the right structure to solve the problem we're trying to do in the most efficient manner. So we have to understand how they all perform, what they're good at, what they're bad at, as sort of and some of the trade-offs here. So if we want to build out our own map here, so we'll write a class for, this is our, what do we call it, hash map here. The idea with a hash map is we need a place to store values very quickly and find their associated, we need to store the key and find their associated value. So we're going to have our init method here, so we can make an empty hash map, and what we're going to store these things in is a Python list, which seems a little funny, but we're going to use a list to store these values here. So we can make our self dot values, this will probably be our data, data is probably better here, is a list. And we want this list to be a certain size. So there's a couple shortcuts you can use. You can say, hey, I want a none times some value here, like let's do none times 10. This should give me 10 nones in a list here. It is now I have got 10 nothings. And none is that special value. That means, hey, there's specifically nothing here, right? Not just the default value, because we can't just have a list of size 10 unless we've added 10 things to it. But thankfully, none is technically a thing, even though it means it's not a thing. It's a little bit silly here, but we're going to put 10 blanks in at this point. We've got a place to store a bunch of values here. And then we'll probably track how many items we have. Our number of items is 0. And then as we store these things, we need a way to have a key and an associated value. Right? So we can have an inner class here for something like, I don't know, a pair. And then its init method can have, if you give it a key and a value. And now you can technically give keys without values, right? So we could have value default to none. So if you have to give me the key, great. You don't have to give me a value if you don't want to. Then we can set self key as the key, and self value is the value. And then with this pair, the idea is I need to be able to compare pairs to see if they're equal or not. So we can define an equals method to say, hey, does this pair equal another pair? And for our case, we only care about the key. Right? I only need to know, does the key match? Because when we use Python dictionaries, we give it a key, and we're either adding that new key value, the value associated with that key, or we're updating the existing value associated with that key. So all we need to care about is, does the keys match? So we can return my self.key is equal to other.key. And there's probably some better checking. The book will have that, the better checking. Hey, checking if we're the right type here. Are you also a pair? That sort of thing. We're just going to cheat right now, and that's okay. We can come back and clean it up later. We just need some of the basics. And then not equals, right? Not equals is turn not self equals other. Right? Take your shortcut here. You don't have to do the same. I mean, this one's really easy. We can compare the keys, but we could also compare ourselves and just return not that. That's our shortcut as we're comparing these things. And like you're going to be doing for your exercise when you compare your polynomials, right? Once you know if they equal, it's really easy to see if they're not equal because it's just not equal, right? That's our shortcut here. All right, so we can have a pair. So to add a value then to our data, we have to do a couple things. The idea with this being a hash map is that we're going to do some really cool arithmetic and generate a value for this key that is unique to the key. And this gets a little bit deep in terms of how this all works. Oh, I forgot to bring up chat. Sorry, one sec. Should make sure I'm watching chat here. There we go. Oh, and yesterday was Giving Blue Day. So we got another Twitch payout, like perfectly on time to give to Giving Blue Day. I don't think we won any extra awards, but I did update the channel. I was super excited, and I saw totally off topic here, but that's okay. So we are at $550 donated to the scholarship fund since I started doing this on Twitch. So it's not a lot of money, but like it's money that wouldn't have been there otherwise. So I feel like that's kind of fun. So all right. Anyway, to find out where we want to put a key in my list of data here. Now, the goal with dictionaries is that they're really quick, right? I don't have to go and look at every value in my dictionary to see if another one exists, right? The performance of this to go and find a value associated with the key is constant, which is really cool. Like, how do we get the value associated with the key in constant time without having to look at every value in this list here, right? Or how do we add a value to the dictionary in constant time? Right? That's better than anything we've done before, right? If we can say we can add things at constant time, we can read things in constant time. Now it's not sorted, so like the priority queue was nice because we kind of got this stuff back in sorted order. This is not sorting anything, but we can get constant adds, constant updates, constant deletes. And to do that, we use some arithmetic and do this thing known as a hash. So all of our values in Python can generate a hash. So let me just go add, just go in here, it's a hash of, say, 10. So anything, there's this built-in function called hash in Python. We'll print the hash of 10. We can print the hash of test. We can print the hash of, what do you want, like 42.5. We can print the hash of let's do a list here. Let's do 10, 1, we'll do 1, 2, 3. So I print these hashes of all these values here. Let's see what we get. Unhashable type list. All right. Well, it worked till we got to the list. So lists can't hash. So if we were to try and make a dictionary here, so we'd say here's my values is a dictionary, and we'd say values key of, what key do we want to give it? Let's give it a some list here is 1, 2, 3. I don't know if we've ever tried this before. So hey, the key is my sum list. The value associated is going to be 1. Right, so we pause. Oh wait, we got rid of that one. Okay, good. So we run this one here. You get unhashable type list on your trying to use this as a key? Well, that's interesting. So not everything in Python is hashable. A lot of things are, right? Our integer, it hashes to 10. That was really easy. Test hashes to, I don't know what this is. 42.5 hashes to, I don't know what this is. But that's fine. And every time you hash those values, you generate the hash for them, they'll match. So the rule is the value that you get back from the hash will always be the same. Now, it's not the same as last run. Notice this is not a negative number anymore, but it's consistent while my program's running. So it is going to generate a unique value for this here. And it's a repeatable unique value. So the idea with a hash is that you need to be able to generate a unique value from your object. And it has to be the same unique value every time. So when you think of things that you can hash, lists aren't going to hash because they are mutable, right? The list can change. So if I were to hash a list of 1, 2, 3, and then change the list and generate a hash again, I would get a different hash value. Even though it's technically the same list, we've changed what's in the list, and it's going to mess up how I hash it. But if you have tuples here, we can do a tuple. You can hash a tuple because tuples are immutable, right? So if we were to print the hash of some list, really it's some tuple now, but we could. The tuple is immutable. So you can generate a hash from it because the value that you're going to get, and we're going to look at all of these added together essentially, or some sort of interesting arithmetic with these values here, it'll be consistent. So if your object is immutable, it's very easy to hash it. And you can pick all sorts of interesting strategies for hashing things. Generally, you just add them all together. There's all sorts of smart ways to do these things, and people have written whole papers on how you hash things efficiently and all sorts of fun stuff. But our general rule here is hash should be, or must be, right? Hash values must be mutable for objects, meaning the hash value should not change here. So that gets tricky if objects are mutable or changeable. I don't know how to spell immutable. Immutable. Oh, all right. I don't know where it had the double letter. So if we wanted to go and write our own class here, then let's do like a class for something easy like student. We could define an init that takes how about a name and a score. Self name is the name and self score is the score. Right, and that's all we have for now. That's fine. So if we wanted to make a student, so student equals a student, even Eric, and I probably have 100% because I'm grading myself. Right, you can do that when you grade things. You can give yourself any score you want. So if I take my values dictionary key of the student and assign it, I don't know, something else here, doesn't really matter. It's okay. No worries here. It doesn't fail on me here. But now if I want to go and say, let's print values here, let's see what we get out. We get, okay, hey, there's a student at this memory address, essentially. The associated value is 10. Sure. Now let's go change my student, and let's say my student dot name. Let's put in my full name here. We can be Eric Chinesky. And then we'll print the values again. We'll run that. Okay, sure. Still the student at this memory address. Right? The object hasn't really changed. We've changed values associated with it, but it's at some memory address. But now, what if I want to make another student here? Let's do a second student equals a student given Eric Chinesky and 100. So we'll make a duplicate of me. Right? And let's take our values, key of the second student, and let's associate another 10 or something, right? And we'll add values. Well, now I have two students in here. Right? One's at FFD0 and one's at FDC0. So different memory addresses. They're pretty much the same student though, right? They have the same name, they have the same score. All right, well, that's not working exactly what we want. So let's go add in here an equals. Let's see if we can make one student check to see if it equals another student, because I kind of would have expected it to update the associated value. We should probably change that associated value. Let's do that to like 100. Let's see if we can make these equal. So we'll say self dot, or we'll return self.name equals other.name, and self.score equals other.score. Right? So if the names match and the scores match, we're equal. Then we can define not equal, or not self equals other. Now we get an error. We didn't do anything about hashing here, but all of a sudden we have an unhashable type. All we did was add an equals comparison here. So what happens behind the scenes is these are sort of connected. Once you have an equals method, and we've overridden how we define if something equals, it's no longer getting the default hash value. Remember, all of these things, like they're overriding the defaults here from the object method or the object class. Remember, we inherit everything from object, so we get some default value. So the default equals comparison says, are you the same memory address? I have no other way of comparing one object to another object if it has all these properties, except for, are you the same location in memory? That's the default comparison in object. But now if we're saying, oh, okay, maybe you have two different students in memory, I don't care if they're in different locations in memory, I care if their values are different here. So we're going to override equals, and all of a sudden we can't hash it because the default hash depends on the memory address. And if we're changing what we're looking here, this is no good. So the rule when it comes to hashing here, right? They must be immutable for objects. So if two objects hash values match, they might be equal. Two objects equal, and must have the same hash. Objects. There we go. Come on. So the idea is that you have to have the same hash if you might be equal. But if you are equal, you have to have the same hash, because the idea is if I take one object and if it's supposed to equal another object, I need to get that same hash value back out, because I need to be able to go and use that hash value to find where it's going to go later. Hector, my friend, thanks for donating those bits to the Student Scholarship Fund here at the University of Michigan Dearborn College of Engineering and Computer Science. You, my friend, are a legend. So we use this hash value in a hash map or a dictionary to find where it's going to go. We mentioned there's some quick arithmetic to get us that performance of O of 1, of constant time performance. So when we're going to go put something in a dictionary, we're going to go get the hash value of it and find out where it's going to go in our storage here, this data storage. So if you want to go add a value here, so we're going to define, oh goodness, which one is it here? This is why I need to go copy off the book. Let's see. I think it's add, no, not other. Where is it here? It's one of these. Not the delete item. Something about item. I think it's get item. All right, I'm just going to go copy off the book here. Apologies. Let's see. Nope. School 3. There it is. All right, so this is our maps. Here we go. Yeah, map of a value. Get item. Yeah, it is get item. Okay. And then set item. Set item. So to set an item, right? So here's your map of a given key, assign a value, right? We want to do that. So that's our set item. Set item, given a key and a value. And again, value could be none, right? It's okay if value is none. Not too big of a deal here. If you want to always require it, it's okay. It's totally an option here. So what we need to do is to get the index location of where this key should be. Right, so our index is going to be the hash of the key, which will generate a consistently unique value for this object, modulus the length of my self data. So if my internal storage here has 10 slots, take this hash value modulus it by 10, I'm going to get 0 through 9. I'm going to get an index. Now, this is actually a really bad value to use. There's really cool math that people have done. Turns out things like prime numbers work out really well for this sort of stuff here. We'll get to that in a little bit once we start talking a little bit more about the math. Okay, but just it's bad. It's easy for us. It's easier for us to look at and conceptualize how this works. So we'll just mod 10 and say, okay, this is now your index. This is where you're going to go. Cool. So then I can go look at self data. So if my self.data at the index is none, great, there's nothing here. If there's nothing there, I can go add you to this location here. So we'll take self.data at the index, then can equal self.pair. Right, we wrote that pair class here to store keys and associated values. We can give it the key and the value. Right? If it's not none, then what do I want to do? Here's where we get into trouble. So the idea is that I keep this oversized table for my data, this oversized list for my data, so that I have room to find these things. Now, hash values are going to be consistent for an object, but two different objects could have the same hash value that are not equal. And because I'm modulusing by my data here, obviously there's only so many different numbers I'm going to get out for an index. So it's possible you give me a key that generates the same index that is not equal to what's currently in there. Does that make sense? So I might get something different. So what do I want to do for that? So I need to see, well, this spot's taken. Where should I go next? And now the easy way to go about that is you actually make a list instead. So instead of this being just a single pair, we're going to make it a list here. So we can say, hey, let's make a list given a pair. And then I can just keep on adding these values to that list. Now, the most efficient way, you actually do a singly linked list, because a Python list has a little bit of extra overhead. It has more size than we really need, so it's taking up more space. So I think the most efficient way the book gets into it is doing singly linked, essentially like a bucket. So we'll say, okay, this bucket has room for all these things, and I'll add it in, and it knows what its next is, and knows what its next is. That's a little more complicated than we care about. And we're not actually going to use our own map, because Python has a dictionary. And the really smart people who wrote Python and looked at Python and said, yes, this performs really well. The odds of us improving that, well, let's be honest, are probably like that, really. I shouldn't even open my fingers at all. The odds of us making Python perform better at this point here. Not to say in the future you can't improve Python, but what we're doing here, in our second semester of learning how to program, they're like actual zero. And that's okay, right? That's fine to admit we don't know how to do that sort of thing. So I'm going to make a list. So if it's not none, it means there's a list here. So now I need to go and see for every item in that list. So for item in self data at index, right? Because that is a list. This is really for every pair, right? That's in there. Now there's going to be a list of pairs. Do you want more comments here? So start a list with one item, one pair. Is that useful? Okay, you just got to shout at me. I'm not allergic, but I tend to avoid comments. What's averse to comments? That's the right word there. So for every pair that's in here, we need to see, did we find a match? Right? Okay, sure. So if the pair.key is equal to my key, then we match. Right? Whatever that key was, fine. If we found a match, then I'm going to change the value. So I'm going to say, hey, my old value, then, excuse me, we can say pair.value is equal to the value. Change the value. And then what we want to do is we want to break this loop. We're done. Or really, we could just return. That's it. We're done. Right? Game over. If we've gone through every pair and we haven't found a match and we haven't returned, I can go add to it. So I can take my self.data at the index and I can append a new pair. Self.pair, give it the key and the value, and then take my self.number of items plus 1. Right? Because we added something new. So set item will add or update. Right? In a Python dictionary, you can add or update with the same syntax. So we've either updated, we haven't changed our number of items, or we've added something new, we've changed our number of items. And this, I guess this one should also be self.number of items, right? Number of items plus 1, right? So either we added something new, or we've had to go through, find that it wasn't in that list here, and we went and added it in. So I can go set an item. We can define a get item. So if you give me the, really this is should be the value associated with it, right? The value associated with the key get item here. Otherwise it raises a key error if it's not there. So we should call this the key, right? I think that's a better term for it here. So we need to get the hash value, right? So my index is going to be my, and now this is not crazy arithmetic here, but I feel bad having it twice, right? Wouldn't it be nicer if we just had like a helper method for this? So we can do that. So let's go, let's refactor and introduce a extract as a method here. Let's get index, or what, index in hash table. I don't know. Sure. And yes, we want to replace that one as well. Look at that. Index equals, and that should probably be a private method. I named that one badly. So we'll call that index here, and then we can return the index, or we'll just return that, right? Return hash of the key modulus the length. So then we have our index equal to, okay, we didn't save a whole lot here, but we're going to use this a lot. I feel better that it's a function. So we'll get the index, and then we're going to look. So we'll say, hey, if my self.data at that index is none, we can raise a key error, right? This key doesn't exist, right? Key not found, there's something in here. Otherwise, if this didn't happen, then I could say for pair in self.data at the index, if my pair.key is equal to the key, you can return the pair.value. Right? Again, looking at every pair that we're storing in this bucket, essentially, if we find a match on the key, return the value, because we want the value associated with that key. If we've done all of that and we didn't return something, we can raise another key error. Right? We found a bucket based on that hash, but it didn't have a match to that key. Sure. Okay. So a couple funny things here. The idea that Python dictionaries perform, right? We talked about performance a little bit here. So this is technically, should be on average O of 1. And there's a big old star here. Big star here. Same with set item here. So this is on average, right? So our average performance O of n, or I'm sorry, O of 1 with a big star. Okay, so this is average, right? This one's average. Now, the big star here is assuming that we have a uniform distribution of hash values. It's not always the case, so it depends on the data that we're using. So we gotta do a little bit of hand waving and say, you know, it should perform this well if you have a good distribution of data. We don't always have a good distribution of data. Sort of depends on what the data is that we're storing. Like, so you saw the index value, or the integer of 10 hashed to 10. So if we were going to store values in our hash map here that does not do smart things like, so this is always using 10 as our size. And again, we'll get to fixing this in a minute here. We can do a little better here. If I wanted to store 10 and store 20 and store 30 and 40 and 50 and 60 and 70 and 80 and 90 and 100, and they hashed 10, 20, 30, 40, 60, 70, 80, 90, 100, and I'm always doing mod 10, they're all going to get the exact same hash value. So of my 10 slots here, I'm only using bucket index 0, and all 10 of them are going in here. Am I going to have constant time performance if I have all n items in one bucket? No. So the bit of hand waving that we do here is, you know, assuming uniform distribution of hash values. Now, again, things that you can do, like use a prime numbered length for your internal storage, increases the chance of that uniform distribution. Smart people have written papers on this sorts of things, and other smart people have looked at them and said, wow, that's really smart. That's awesome. I can't even read those papers, I'll be honest. Like I looked at one time because I was like, this is really interesting. How'd they come up with that? And I got lost after the introduction. That's okay. I'll try and stay in my lane. So that's one thing we can do is do proper distribution here, proper sizing. The other thing that could happen though is we can do dumb things. And if someone does a dumb thing, you can only help them so much here. So you can define a hash function here. The hash function, right, is supposed to return a consistent hash value. So if I said return 1, do I have a consistent hash value for every student? Yeah, no matter the name, no matter the score, I'm going to get a consistent hash value. Do I want all the students to have a hash value of 1? No, that's bad. So we've done a bad thing. Everything will get put in the exact same bucket for every student that I'm storing in a hash table, my dictionary. But we did the bad thing ourselves, so that we have to be careful. So one thing that you would do, if you wanted to be able to hash student, you can only hash things that are immutable. You don't want to hash a value of name if name is mutable. So we can just, let's return this. We'll say return hash of name plus hash of score. Self.name, sorry. Self.name and self.score. Right? We can do this here. This is real bad. So this is bad because your name and score can change. So what would happen then? So I added the hash value. I should now be able to hash a student here. Let's see if it runs for us. So we have a student at this memory address. We have a student at this memory address, the value associated at 10. Then we had another student, value associated at 100. Sure. So let's see. So we took student, we added it in. Then we changed the name of that student. So let's go take values of student again here and put in 20. So it's the same student, right? It's the same student object, right? Let's go run this. Now I have this student at FD0 is in my dictionary twice. Because the hash value we generated is different, despite it being the same student. So because we used a mutable value, now I've got this orphan thing in my dictionary. I'm never going to find this one ever again. Because student does not match this location here. It's out here in the dictionary. I'm never going to be able to find it again. So it's just taking up space. So hashing on something that is mutable is really bad. Don't hash values that are mutable. If something's going to change, don't use it as part of your hash. So we want to use something that should not change. So maybe we say, hey, you can't change name. We'll say, hey, name is going to be private here. Score can change, right? You're allowed to change your score, and that's okay. So we'll say other name, other score. And all we're going to do is hash the name because this should be immutable. We said, when you create a student here, you give me the name and I will assign it to my private value name. I'm not going to give you access to change it here. I'm not going to write a public set name method function here so you can go change name. If you go change a private value, you did a bad thing, you shot yourself in the foot, there's no helping you, right? But you should not change the private value. So every time we hash the student, we should get back the exact same value every time. And now for equals though, right, I might have two students with the same name with different scores. This is a little bit of a toss-up, kind of depends on what you want to do here, right? Should they be equals just based on name? Or should we also look at the score? Is it possible to have two Erics with two different scores? That's possible. We probably did a bad thing and should have had another unique identifier because name is not a great unique identifier. Like if we had a student ID number, that's probably better because names can change, right? You can go change your name. So I think all of this is probably bad. So let's just say, let's do ID, name, and score. And then we'll say private ID is the ID here. And we're just going to hash the ID instead. So we'll take your unique ID number, and then to compare for equals, I'm just going to look at the ID number here. I don't care what the name and score are. If you have the same ID number, you've got to be the same student. Then maybe you went and changed your name. Maybe your score changed. That's okay. We're just going to compare ID numbers here. So if you want to go change your name, fantastic. You can go change your name. If your score changes, that's fine. You can change your score. But now when we go and change Eric here, let's see. So we said, hey, here's your student. Oh, we got to give it an ID number. So this is student ID number 1, right, of Eric. Then we'll go change student's name to Eric Trineski. Make another student. This is student ID number 2. Let's do 1 again. So we'll make another student in memory with the same ID number here and see if we can't update that associated value. See what we get. Now the map behaves, I think, like we'd expect. Right? We said, okay, hey, this student here, student ID number 1, let's associate a value of 10. Let's change the student's name, change the value associated to 20. This works because this student matches the other student. They have the same ID number and they hash to the same value. Right? That rule about hashing, if the values are equal, they have to have the same hash. And that's what didn't work before, because before we said they should be equal, but they didn't have the same hash. Right? Because we were hashing the bad things. So we're changing it. That's good. And then we go make a new student with the same ID number here. Let's change the name back. Maybe just Eric C. and change the associated value. Update our dictionary, and now the value associated becomes 100. Now notice the memory address hasn't changed. So interestingly, we didn't go and put this new name in here. So I made a new student and said, hey, Eric C is the name. But if I were to print the values, I want the key here, right? So I want for key in my values dictionary, let's print the key.name. It's not going to have this new name. Remember, the idea is if this exists, all we're doing is updating the associated value. We're not updating the key. And we said, hey, these match because they have the same ID number. So I'm going to get the Eric Trineski name. Oops. Tuple, key value.keys. There we go. Keys. I just want the keys out. No. Shoot. Object has no attribute. Oh, I added a couple things to the dictionary here. That's right. If key is equal to student, print the name. Let's see if that works. Okay, there we go. So now we can get the name back out. So the name Eric Trineski is this one because I updated this student's name, Derek Trineski. So you have to be careful. So this gets a little complex. So using dictionaries is a lot of fun, especially if you start using custom objects. So if you want to use your own class as a key in a dictionary, there's a lot of gotchas. Right? We have to make sure we have a good hash value here, a good way of hashing off something that is immutable. Right? It should not change. And then make sure that we're comparing our equals and not equals efficiently as well. So should work the same with our own hash table here. So let's give it a try. So let's see if we can do our data is a hash map here. I'll take our data index of the student, right? It's going to equal 10 or something. And then I don't think we can just print our data though, can we? So let's see. I think we need to add a string here. So to our hash map, let's see if we can just define a string version of ourselves. We'll return string of self data. How about that? That's not going to be the prettiest thing in the world, but this should give us the representation of what's in there. We'll see what we get. And then let's see if we can print our data. Let's give this a run. Okay. All right. So the none, right? We have a bunch of nuns. Somewhere in here, there is a list of pairs. Okay. We're getting closer here. Right? Sure. Do we want to see what's inside of that pair? We could probably do something like that. So let's say, we probably want to skip the nuns too, right? Or do you like seeing all the different nuns or seeing all the different things that are in here? Because we should be able to add a bunch of values. All right, so let's have a result. It's equal to this, and for value in self data, take our result plus equals the value. Let's see, what do we want to do here? We start with that. plus a comma and a space. We can add all those in, and then when we're done, we can take a result plus that one, right, ending that curly brace. I think we can do that. And then we'll return the result. Let's see. Oh, goodness. None type and string. Oh, if it's none. So can we do a string of value? There we go. Okay, so we're getting close. And we get a little extra trailing one here, so I guess it's a little ugly here. So let's do results. How about sliced to -2? Right, to cut off those last pieces there. Be a little prettier. Oops, does not support item assignment. Oh, shoot, that's right. Okay, so results equals result sliced plus that. All right, maybe we can do that. All right. Now we need to get the pairs, though. So what do we want to do with our pairs? So we can make pair have a string representation of itself. String. So we can return key plus value, or it's plus colon plus the value or something. Self.key and self.value. See what we get here now. Oh, why didn't I give that to us now? Okay, that's fine. So let's see. So did the string of the value should have been the pair, right? Why did it still give us that though? Wouldn't have done the string of that. String of the value. Oh, because it's a list of pairs. All right. For pair in value. Oh, this is getting ugly now. We'll take our result plus equals string of the value. Get that now? Non-object. Okay, so if value is none, we take a result plus equals string of the value plus that. If it's not none, then we can add them in. This is a lot of work here. I'm sorry, just to make this print out pretty. Oh, it's still doing the pair objects thing. Didn't we get these? Oh, string of the pair. There we go. Oh, student and string. Okay, we're getting close. We're getting close. So we want the string of self key plus the string of self value, because we don't know what these things are. So we'll force them into strings here. All right, okay, we're getting closer. So now we have a student object here. Well, now maybe a student could have its own string here. String. What do we want here? Like name colon the name. Or we need the ID number too, right? So we'll have ID self.id, name is the name, and score is self.score. Right? Nice formatted string. There we go. That saves a lot of time. All right, we got it. So now we have ID1, name Eric, score. Oh, but this is not a list. So if it's a list, so if it is a list, we want to take our result plus equals an open list, right? And every one of those, and then take our result at the end of that, right? Because we want to add in that nice representation to show that this is a list here. Plus we want the comma, no space. All right, now we have one student in that bucket. Hooray! All right, so if we make another student and we want it to get into bucket number 1, if the ID number that we're hashing, right, is say 11, we should be able to add it in, and it should end up in the same bucket. So let's make a student. Let's make student a student 2. Student given, so if the ID is 11, right, it should hash down to 11, and 11 mod 1 should give me 1, so it should show up in the same bucket here. 11, this can be Jeb, and his score is like 75. Then we'll take our data, index of student 2, equals, I don't know, there's some number here, the associated value doesn't matter much. We should be able to print our data. We should be able to get 2 students in the same bucket. There we go. So 2 students in the same bucket here. If the ID number is different, say like 3, right, it should land in a different bucket. Here's Jeb in bucket 3. Here's me in bucket 1. Right? So you can kind of see they're landing in these buckets as we go. All right, all of that just to visualize it. Was that worth it? That was worth it, right? Okay. So we did the get item, we did the set item. We can delete an item. Sure, deleting an item. Now, this gets a little tricky because we have to remove it, but it should work out pretty well here because we can delete something from a list really easily, and we're just using a list for storage. Works out pretty well. So we can define a delete item given a key. So we need to find which bucket it's supposed to be in, right? So the index should be my self.getIndex in the hash table given the key. And then we can take that bucket and delete it, or if that bucket is none, I guess, right? So if my self.data at the index is none, and raise the key error, right? Otherwise, we want to go through and see if we can find this one in here. So we can say for pair in self.data at the index, if the pair.key is equal to the key, right? Or really, I think, do we add this in? So if a pair equals another, I would have to make another pair. So we don't want to make another pair, that's fine. So if the key equals the key, then we want to delete it. So we can take our self.data at the index and we can call remove. Is it remove? I think it's remove, right? Given the key. Oh no, that's not going to work because it's going to look for a pair. So we need to make a pair, right? So a self.pair given the key, and we don't care what the value is, right? We just want to remove that pair, and pair should be able to say, okay, hey, I'm equal to because my key equals the other key. I think that ought to work. I guess we could make the pair first, right? So let's do that. So we'll say, here's my, I don't know, the item, self pair given the key. So if the pair, now we can just compare if it equals the item, remove it, remove the item, and then return. If we've gone through, we haven't removed something, we can raise another key error, right? You shouldn't be able to delete a key that doesn't exist. We should be able to go and delete a student here then. Let's see if we can delete student. Take our data, what do we want? This is delete, right? The delete our data of student 2. Right, now if we print it out again, it should be gone. Yeah, so deleted. Oh, did it put back? It didn't put back a none though, because the list was empty. Shoot. So if the list was empty, we removed it. It should be okay, right? Why does it? Okay, so we can have an empty list, I guess, an empty bucket. I think that's probably okay if we have empty buckets. Let's see, because we're depending on if it's none. So if the data is none, if it's not none for set item, right? Set item. So if it is none, go ahead and add an empty list. If it's not none, we'll just append it. Appending should be fine in an empty list. That should be okay. So I think it's just our print is funny here. We print ourselves. So, oh, because we were assuming it would have an item in here. We did this result stripping thing. That's probably why. That's a little ugly. I'm not going to worry too much about it. Is that okay? All right. So we can delete an item. We can get the length of something, right? We're tracking our number of items. So when we delete something, right, we need to make sure we've removed it and then take our self.number of items -1. So then to return a length, we can just return our self.number of items. Awesome, we got length. And then iterable of our self. This idea you can say for key in the map here. This one's a little tricky, so let's go see if we can steal theirs here. And then we should be able to support in the get, set, pop item, clear, keys, values, all sorts of fun ones here. Let's see. So do we have, I think we've got it here. Let's contains. Oh, if we contain a key, right? We can add contains. That's cool. That's funny. What a funny way to see if we contain. Just use get item. And if there's a key error, return false. I feel like this is bad. You shouldn't use exceptions, but that's not proper. Let's see. So yeah, the item, keys and values, equals, not equals, less than, sure. Where's our iterable? There we go, iterable, for item and table. Yes, this yield, this is what we're looking for. So yield is a really cool keyword here. It will give back the value and then wait for you to ask for the next one. So that's what we want. So we're going to define iterable, before. Now, this gets weird because remember, dictionaries don't guarantee order. And I think you can see what happens here. We don't guarantee the order here because it's based on whatever index it shows up in, right? So if I want to give you items back out, I'll give you every pair then, right? So we want for, this is, I don't know, bucket in my self data. Is it okay if we call it a bucket? If the bucket is none, we don't do anything, or is not none, right? If it is none, we don't care. We're just going to skip that bucket. If it's not none, we can yield, or no, we want to say for item or pair in bucket. In the bucket, we can yield, use our cool yield keyword. And now we want to give them back as a tuple, right? I don't want to give them a pair object or our pair class because they don't know what a pair is. They just expect a tuple. So I'm going to yield a tuple of the pair.key, comma, pair.value. What's written behind me? Oh, I don't actually know. I don't know what that is. Not entirely sure. So we can yield the key and the value. Oh, I guess we don't even need the parentheses, right? It'll tuple that for us. And it'll go to the next pair and the next pair and the next pair. When that bucket's empty, right, we'll go to the next one and go to the next one and go to the next one. So you should be able to iterate over all the values in here. Now, the other piece we haven't done yet is what if I add a bunch of students? Oh, is it really? Is that Arabic? No. Oh. Okay. I did not recognize that at all. I barely know English as it is. So languages with alphabets that aren't, what are the Latin characters? Is that what those are? Right? I have no idea. My wife learned a little bit of Amharic when we went to Ethiopia. They have a completely different alphabet, and she also learned a little bit of Ukrainian with the Cyrillic alphabet, which is similar, but some of the letters have different sounds, and that's really confusing too. And she also knows a little bit of Hebrew. Like, I don't know how she keeps it all in her head. I just get dizzy looking at stuff like that. So that's really cool. All right, anyway, so if we go to add like 50 students, what happens to our buckets here? Are we going to get good performance? Even if we have a good uniform distribution? No. So the idea of getting that good performance also relies on our total storage being larger than we need it to be to make sure we get a good uniform distribution. So there's this idea of a load factor. I don't know who came up with it. Really smart people did. So you might have a load factor and say, hey, how full is too full? And I think somewhere around like 75%. I don't entirely remember what it is. I'm sure it's in the book here, but I'll say 75% is my load factor. So when I go add an item here, that's my set item, right? If my load factor is too large, what I want to do is rehash everything. And this is a bit of work, but it's okay. It's doable. So let's check that probably before or after. I don't know if it matters at all. So we'll say, hey, if the length of self is divided by the length of data, right? Because the length of self is how many items we know we've put in here. The length of data is how large my overall number of buckets, right? How many buckets do I have? So number of items divided by number of buckets, right? So if that is greater than my load factor, I need to go rehash everything. Oops, colon over on this side. So I'm going to make this a private helper function. This will be rehash. So the idea with rehashing is I need to increase the number of buckets, and then I need to rehash everything that's in there to put it in the new bucket. Because when you get that index value, right, my self.index value, where's that helper method here? It's based on the length of my data. How many buckets do I have? Right, so let's go through. So in self.define rehash, I need new storage. So I have a new data equals none times the length of self data. I'm just going to double. This is not proper, right? This is lazy. Won't give good distribution. Right. The idea, if you have like a prime numbered value here and you double it, you're not going to have a prime number. So finding the next prime larger than your doubling or something, like there's really fancy ways of doing this. That's okay. We're doing the easy thing. It's okay. We don't need to do the really good stuff right now. So I have the new data here, and I have doubled the size of the old one. Okay. Now, actually, this might be easy. Let's do it this way. Let's say old data is equal to self data. Let's save off the old stuff. Okay. Then we'll just change data here. Self.data is equal to none. Oops. Oh goodness, I lost it. Hitting the wrong keys here. Where did I go? Rehash. There it goes. None times 2 times the length of old data. I'm glad you know this stuff. That's awesome. Thanks for joining along. So we're going to create a new set of buckets, right? Double the length of the old one. Then we need to go through and find everything in the old data, right? I guess we could have used our iterator here. That's okay. I think we'll be all right. So we're going to say for this is bucket in old data, right? For every bucket in the old data, if the bucket is not none, then we're going to go through for every pair in the bucket. We need to go and add it to ourself, right? We need to go take that value and put it back in this new location here. Now we already know how to do this, right? We have a set item here that uses our self data bucket. Pretty nice here. The problem is this is going to count for us though every time. So we don't want to be adding new items here essentially, but we know self data is empty. So we're going to cheat a little bit. So I'm going to say for every pair in the bucket, I'm going to take and re-add myself here, but I don't want to redo the work. So we're just going to call add again. So we can say self, can I say key of? I think pair.key, pair.value. And I can take my self.number of items -1. Don't double count it. Or actually, okay, that's even more work we need to do. So we'll reset it here, and we'll take our self.number of items. We'll just set it to 0. Right? We'll go back to 0, and then as we start adding new values here, we should be good to go. I think this syntax works. Let's find out. I don't actually know if it does or not. But should rehash it, I think. So as I start adding values here, then it should get larger and larger and larger and larger, right? To make room for all those new ones here. So let's skip all the student stuff here for now. Let's just make a new hash map here. This is some numbers, right? There's a hash map here, and let's get a bunch of random values. So for number in range, let's do like 30 values here. Let's generate a random number and add it in. Or we can just do the number too then, right? So let's take our numbers, key of number, right? Equals number. Sure, why not? We'll go add it in. Go assign it a value. And then we'll print numbers. So we should see this working, I'm hoping here. All right, so the first time, right, we have 0. Associated value of 0. 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6, 7, 7, 8, 8, 9, 9, 10, 10. And then Oh, that was, oh no, yeah, so it resized here at 7, right? Once we were greater than our 75%, we resized. Now we have 20 slots. So we just keep on going here. Now, they rebucket themselves really nicely, right? So I think that's why the random numbers might be a little bit better here, but that's okay, right? Because they're all going to stay in their bucket based on their index. Right, so we never have any duplicates. Let's do random numbers. That might be more fun. So let's do numbers index of random.randint. I don't know, what do you want to do, like between 0 and 10? Or was it random? Random.randint for next. Randint 1 and 10? Is that what that one is? You have to import it? No? Wow. Do you have to import random? It's been a little while since I did random numbers. Import random? Now is that happy? Okay, random 1 to 10. And then what? Assign associate the value of, we don't really care what the associated value is, right? We'll just say 0. Probably okay. And print it out. Uh-oh. Well, that didn't work. Oh, because we're overriding the keys. Shoot. Okay. It's sort of working, right? We get a 6, we get an 8, we get a 10, we get a 2. So eventually they'll start replacing themselves, right? Every time there's a duplicate, because it's the same key, we're just changing the associated value. That's the problem. Shoot. Maybe numbers isn't good here. So I want it to show that the buckets get bigger. What should we do? I guess integers are no good here. Can we take that and then what if we divide it by another number? I'm trying to think of how to get a nice random number. This is not working well. Okay, so random value random.randint from 1 to 10 divided by random 1 to 100. I think that'll give us some interesting numbers probably. And then we'll take our numbers index of the random value here, which should be okay. You can give it any sort of key, right? And it should hash to some interesting value. And then let's assign it a value of, we probably don't really care about the associated values. See what we get here. All right, this looks more interesting here. Do we ever get more in the same bucket? Yeah, okay, look, so we get some in the same bucket here. There we go. That's what I was hoping for. So you can see, and it's a pretty good distribution, but not uniform. It's not every time we're getting a different bucket here, but that's okay, right? It should work out. So this time, this value and this value were here, this one was over here, but we make room and resize ourselves to fit eventually here, and we get a bunch of values in here. There we go. I shrank it down a lot, but a bunch of nuns. This bucket has a bunch of numbers here. Look at that. Again, we're using a bad value here. Power numbers that 10, 20, 40, like with a 0, they don't mod very well, but that's okay. We don't care too much. This was a better example, right? So you can see we just keep making room. Now, as we start deleting items, we still sort of have the same issue, but opposite. Eventually, if we start taking out all the values, we're going to be way oversized. So you might have a max load factor and a min load factor and be able to shrink yourself here. That's an option. Just depends on how you want to do it here. So your rehash could take a factor and you could give it 2 to increase, and you can give it like 0.5 to decrease if you wanted. Again, we could leave that for another time. Could use a factor increase or decrease size. So when you're removing items, that hopefully would work out well there for you. And then we should make sure we can actually go through and iterate. Right? We wrote the iterator, we never tested it. So for I don't know what key and value in my hash map, my numbers, right? Because I should be able to get out the key and the value here. I should be able to print the key and the value. The order is not guaranteed, but here's all those values we added here, right? So we did 30 numbers. Do we have 30 in here? Probably 30 lines. I doubt we got a duplicate. It's possible we got a duplicate. That is, 29 lines. Oh, no, 29 line breaks. Yeah, because the last one wasn't a line break. So now we should get 30. Right? Yep. 29 line breaks. Did we get a duplicate? Maybe we did. All right. I don't know. I can put it in here. This will count for me really easily. I'm fond of Excel. 27. Only 27 unique values out of the 30. Okay. Interesting. How did they get 30 to 29 line breaks then? 29 line breaks. Okay. I don't know. I'm confused. It's probably okay. All right. So hash maps. Right? We can iterate. The idea with the table, right, is we can put them in these buckets. This is this idea of the bucket array. Here's awesome with our hash function. So hash it, compress it, right, so it fits in our index. All sorts of fun ways to do how these. I don't even understand all these hash code things. It's okay. That's probably more trouble than we care. Immutable types are hashable. That's the idea here, right? We did some of that. Other ways of doing the modulus stuff: multiply, add, and divide. Sure. This separate chaining is what I'm talking about. This is probably the most efficient way. Instead of doing buckets with lists, you actually use like singly linked lists. It's not too big of a deal. And this load factor we talked about. You can do other silly things, and I don't know why it gets into all this, like because we don't do these things. But you can say, hey, if this spot is full, just go to the next spot, which works out really nice until you start removing things, and then you'd have to know, should you backfill items that were previously put further in here, so you have to like track them differently. It's a big headache here. I don't like any of that. But expected time for all of these things, right? Constant time. The worst case is if we do a bad thing and we don't have good distribution, or I said, hey, my hash value is 1. You just have a list, right? And you ignored all the other buckets. So it's possible they perform very badly. It's unlikely, and we do a little bit of hand waving and say, yeah, we always have a uniform distribution. It's not true. Sometimes you'll have data that's badly distributed and your hash map won't perform all that well. That could happen, right? There's not a lot of things we can do to avoid any of that. Yes, our Python implementation. Okay, we should have like capacity and the key value here. Sure. Prime number for the mad compression. Yeah. So this is like the smart one. This is a lot more headache than it needs to be here. The separate chaining, if you want to do the separate chaining, linear probing, we don't want. You could do a sorted map. Sure. Then you have a sorted table. You've got some fun things we can do here. We're not going to get into that. You don't need the sorted map. Because the performance is different in these anyway when you start finding things. And then skip lists are fun. We're not going to get into those either. Okay, so that's about it for the chapter. Awesome. Very cool. All right, so when we come to the lab, we'll practice with our maps and hash tables. We want to write a class that is hashable and be able to use it in our hash table. That's sort of the goal. Like building out a Python dictionary is just copy paste work out of the book. Not all that interesting, but if we can write a class that's hashable and use it in a dictionary or hash map, that's a useful thing. And then next week, we'll talk about search trees. So we've got a couple ways. So we talked about trees a while back, right? And binary trees. So we'll look at search trees, which are essentially sorted trees. And you can find values pretty easily. And then I think the project is due the 23rd, right? Is that the way we landed on? No, the 28th. Right. Okay, so on the 28th, I don't think it'll take us the whole time for search. It might for search trees. There's a lot to it here. We'll talk about the project. Sorting and selection will be pretty quick. So we can talk about the last project solution, talk about the group project starting on the 28th, and then do sorting and selection on the 30th. We might start this early if we have time to give you more time for the final project. So we'll see how that goes. And then ethics, again, probably only one of these days we need to spend on ethics. It's a really cool book you can read. Not that you folks have free time, but it's a really cool book about ways that we've done badly with data, and a better approach to ethics and understanding this sort of stuff might be useful. And then final project work time, and then presentations on the 25th. So again, ideally, if you're done by the 18th, life is better for you. You've got the time if you need it, a little extra time, but you have other things going on. So if we can get it done and out of the way for you by the 18th, hopefully we'll all feel better. Okay, so the lab for ethics, there is an ethics lab. There's no lab here, but I'll come to lab time if you also want to work on the final project on the 18th. I'm happy to meet with you during lab time as well. And then no new lab there, so got a little bit of extra time for the final project. Okay, awesome. Oh, it's 3:16. We almost made it. Thanks so much, and I'll see you on Tuesday.